Hello, everyone. I would like to welcome you to our first webinar of 2025, Introduction to Sinter Brazing. Presenting today is going to be our Director of Research and Development, Stephen Feldbauer. Throughout the presentation, you'll notice up in the top left corner, there's a chat drop down. If you have any questions throughout, please feel free to type those questions in. If we have time during the presentation, we'll get to those questions. If not, all of them will be given to Steve after, and we'll get back to you with those answers. So to not delay anymore, I'm going to turn it over to Steve for the presentation.
Okay. Hey, thank you everyone for joining us today. And as Jess said, my name is Steve Feldbauer. I'm the Director of Research and Development here at Abbott. And what we're going to talk a little bit about today is sinter brazing. And, in the powdered metal process, we're limited oftentimes because we're doing a uniaxial forming process, right? And because of that, some of the geometries are limited. And so it's nice to be able to take multiple components at times, put them together, and have them actually sinter while you're braze together while you're sintering them. Okay. And so that's what we're really going to talk about. And that's why we call it sinter brazing, is that we're going to braze these components together while we're going through the sintering process for the powdered metal components. And so what I'm going to do is I'm going to share my screen here, and we'll get going. So, and one of the things that I really encourage everyone is, please, as we're going, if you have questions or whatever, please go ahead and put those out there, and we'll try to answer them as we go. Okay. Jess, can you see my screen? My slides?
Yes, looks good on my end. If anyone's having any issues with the audio or the screen, again, feel free to drop that into the chat, and we'll try and fix anything on our end if we're able to.
Okay. All right. Well, let's start going through some of the topic. So, like I say, we're going to talk about some sinter brazing, and if we talk about brazing, they're basically three steps that happen during brazing. The first thing is you have your base metal here. These would be your two components that you're trying to bond together. You put a filler metal in here. Either you put it on the edge or you can put it in between them directly. But then what happens is you raise the temperature. Typically, once you hit about 1990, 2000 degrees, depending on your filler metal, it starts to melt. We then flow in, and that material will actually go in and actually form a metallic bond between the two base metals, and give you a good structural bond. Now, but there are some key aspects to brazing, right? And this goes to whether it's conventional brazing or it's sinter brazing. There are some fundamental things that have to be in place to get a good quality braze. Okay, the first thing is cleanliness. Okay, if any of you have soldered copper pipes together before, done some plumbing at home or whatever, you know that the first step is you have to clean those pipes, right? Well, if you don't clean it, when you heat that solder, it won't flow in, right? Because the filler metal, and that would be the solder, or in this case, the filler metal is typically like an AB72 or something like that. When it melts, it won't flow over dirt. Okay, and we'll go into that in a little more detail, but it's really important that we clean the components. And so if you have parts come in that have oil on them, or a rust inhibitor or anything like that, oftentimes the filler metal will not flow over that. So you have to be sure that the parts that you're trying to braze are clean. Okay. Then secondly, is the filler metal selection, right? In this case, where we're talking about sinter brazing, there are other metals out there that you can use for a filler metal. The workhorse in the powder metal industry is AB72. That's short for Anchor Braze 72, comes from North American Hoganess. But Haganese has their own version. Likewise, Chimera has filler metals. So and you can get them in powder form and then compact them, or you could blend them with something and form a paste. So there are different forms of these filler metals, either solid, powder, or paste, right? And then there's the part filler metal chemistry, right? We need to make sure that we're using the right filler metal. Like I said, in the case of conventional PM, AB72 is a leader. However, you can use copper. It's a little more challenging, but you can use copper direct, and we've proven that we can do that. Also, we're going to talk about this in a lot more detail, is the joint gap. That's the space between the two components that you're trying to bond together. That joint is critical. If it's too big, when the filler metal melts, it's not going to have enough viscosity to stand up and touch both sides. It'll just fall down and only stay on one side of the joint, and then you won't get any bonding. Or if it's too tight, you may not get fill, okay? Or if it's too large, also, you won't have the capillary action to pull it through the joint. So it's really critical to have the right size gap. And then atmosphere and temperature. Those are naturally critical to the sintering process, but they're also very important when it comes to the brazing process, because we have to not only clean the part from any oils or things, but before we can get that metal to flow across, we have to remember that all metals have oxides on them, right? And so we have to clean those oxides off using the atmosphere in our furnaces to have virgin metal there on our components that we want to join, as well as on the filler metal. Filler metal has some oxides on the surface as well. So what we want to do is we want to clean those oxides off so that everything is virgin metal and we can flow through that gap efficiently. So like I say, it's really important that we have a clean surface. Surface contaminants, okay, will prevent that filler metal from reaching the base metal and forming a bond, right? It acts as a barrier, and it won't allow us to do that. So we have to clean that. And here's just an example. I mean, if you look here in the lower right-hand side, what I did is I took just a simple pellet of AB72, I put it on a piece of carbon steel, and I ran it through a furnace. And you notice how it melted and it flowed, okay? Well, then I took a China marker, like a grease pencil that you would, it has the little string and you pull it and it exposes the marker, and it's oil-based, right? So I drew a circle around another pellet and I ran it through the furnace, and notice how that filler metal, although it was the same size pellet, when it melted, it would not cross that carbon line because carbon's dirt and it won't flow over it. And the thing to remember is we have lubricants inside of our parts, okay? We have, Acrowax, you have, that EBS, ethylene bisteramide, is Acrowax. You have your Intralubes, Ph.D, Intralube E. There's a lot of different lubricants that are used in conventional PM. Well, what's unique about all of them is once you get above 1,012 degrees or 545 C, the lubricants will actually dissociate. Excuse me. And to kind of put this in perspective, I always use my pasta model, right? I have your lubricant is a hydrocarbon, and it's made up of all these different hydrocarbon strings. And you can think of it as like a big ball of spaghetti that's all wrapped up. And as you heat it up, as you get above 260 degrees C, they start to break down. So imagine if I had a pasta noodle, right? and it's a lasagna noodle. So it's big and flat. Okay, it's made of flour and water, right? Well, I can tear it, and when I tear it, I have linguine. Okay, it's still pasta, but it's a different type of pasta. Same thing happens as my lubricant's breaking down, right? I can tear that pasta again, and I have spaghetti, and then I tear it again, and I have angel hair. But eventually, I'm going to tear it. So I'm going to break it down to the smallest thing I could break it down into is flour and water, right? Well, now I have solid and a liquid, right? Well, in our lubricant, if we keep tearing it down, breaking it down, it eventually breaks down to hydrogen and carbon. Now, what's special about that is hydrogen's a gas. It just floats away. But the carbon is a solid, and that's what stays behind, and that's what gives us that black ring from our grease pencil. The grease is a hydrocarbon. The hydrogen floated away because we got too hot, and it left the carbon ring. Now that carbon is dirt on the surface, and it won't allow that filler metal to go across. So we have to be sure that we get all the lubricant out, especially in that area where the joint is. And here's the thing. This is one of the challenges is if we're going to bond two surfaces together, the lubricant's going to come to that surface and then boil off, hopefully, right? So we have to be sure that we get that lubricant out of that joint and between those two surfaces without it dissociating and forming dirt, or we won't have a successful braze. And so here's you can, this is blown up a little bit. You can see a little bit better how that carbon ring stops the flow of that filler metal. You can see it went right up to it on the right-hand side there, but it wouldn't go over it. And I also did this on a powdered metal part, okay? And so you can see here, I have a ring that's drawn kind of away from that pellet, and then one that's right up against it. And if you notice, the one that's right up against it, the filler metal actually humped up when it melted. It wouldn't cross that carbon ring. And so it's really important to get it clean, but also we have to remove any oxides because, when we talk about oxides, imagine, if I had a plate, a ceramic plate on the surface of every one of our components. And so there's that plate in between. I'm not going to bond the metal, right? And in actuality, that's what we have. When you have iron oxide or, a porcelain plate that you eat off of is just made of oxidized silicon, right? Silicon oxide. And so that's glass, right? And if we have any metal, it will oxidize, or most metals, I should say, will oxidize, and you have that thin layer on it. And so we have to remove that oxide layer to allow that filler metal to touch the components and actually form the bond. And so what we do, the way that we get rid of that oxide is we typically use a gas that contains hydrogen, okay? And the hydrogen comes in, and we want the hydrogen to want the oxygen more than what the metal does, okay? So in this case, we're showing here we have, chromium and iron and oxygen and hydrogen coming down, and it would be like a stainless steel part or even an iron part is the same, right? We have to remove the oxides, and the hydrogen grabs that oxygen. It forms water, H2O, and then the water, because we're above the boiling point, turns to a vapor and it floats away, and we push it out the front of our furnace and get rid of it. And so we can clean those surfaces by reducing the oxides. And so often in our furnaces we talk about, or in our processes we talk about dew point. And dew point depends on the dew point you need depends on the chemistry of the metals, right? And what this is, and I don't want to get into the weeds of free energy and all of that, but the gist of this is, if I look at these lines that represent the energy associated with the oxides, okay, what you find is the lower on this graph you are, the more stable the oxide is. So the more the metal wants the oxygen. So that means we have to have a lower dew point to reduce chromium oxide than we do to reduce iron oxide. So on the right-hand side here, you can see regular carbon steel is actually easier to clean up than, say, a stainless steel that contains the chromium. Now, one of the important things to note is a lot of people in stainless steel, they look at this graph and they say, well, Steve, you tell us all the time that you'd like to see a minus 60 Fahrenheit dew point, but here it tells me that I really only need a minus 50 if I'm going to be brazing at, say, 2050 or sinter brazing at 2050. Well, that's true if we were willing to accept that we're going to clean and try and bond all at the same time. And that's not really realistic, right? To be efficient, what we'd like to do is clean the part as we're going into the high heat, as we're heating up our part, so that when we hit that brazing temperature of 2050, everything's ready and we just finish the process. We'll melt the filler metal and it flows in to the gap via capillary action and bonds, right? So what that means is we want to be cleaning while we're heating up. So now if we come back over here and we say, well, I want to start cleaning my surface while I'm heating up, look, I want to be at like a minus 60 to give myself time to clean up before I hit my brazing temperature. Okay, so that's why you see that. If you look in the literature versus what is used in industry, that's the reason. That's the difference. Okay, and so
Steve,
yes.
Interrupt 1 second. We have a question that came in asking if the oxidation of the filler metal is a concern.
It is, and so just like it is on the surface of the base metals, we have to be cautious and cognizant of any oxidation that is on the filler metals itself. So what's nice though is in the case of like the AB72 or copper, they will reduce similar to what the base metal is going to reduce that. So, but it is a concern. And if you have a filler metal that's really heavily oxidized, it could cause a problem. Okay. And so if we come back to the actual reactions that happen, the way that we make sure that we're going to clean that base metal and we're going to clean that filler metal is we want to be on the right side of the reaction. If we look at this and we just say, okay, well, I have iron oxide, it could be any metal oxide, and we're going to bring hydrogen in. And then what we want is we want the hydrogen to steal the oxygen, form water, and we leave behind the clean metal. Okay. What we have to remember is that reaction can go either way, right? We can use it to clean metal, but if you remember as a kid, you had your bike, and if you left it lay out in the yard, everybody would tell you, don't leave it lay out in the rain, it's going to rust, right? So we can go the other way. A metal plus water will cause oxidation. So how do we keep this going in the direction we want? Well, an easy way to look at this is that arrow that can go either way is like a teeter-totter. And if we have lots of hydrogen, I mean, the metal is the metal, right? We're not changing it. We have to make the part, right? But if we have a lot more hydrogen than we do water, then that would tip the scale on the side of the hydrogen. Nature would look at that and say, I really want this to be a balance. Nature loves a balance. And so what would happen is it's going to run it from left to right, that equation, to try and create water so it would balance out the teeter-totter, okay, or the scale. Now, if we had a lot of water, the dew point's too high in our furnace, well, then we have more water than what we do hydrogen. Nature's going to look at it and say, gee, I don't want all this water. I'm going to run the reaction from right to left to form hydrogen, and we're going to put that oxygen onto the metal. and now we're going to oxidize. That's what happened with your bike in the rain, right? And so what we want to do is always keep it tipped like we have here on the left-hand side, so that nature wants to keep cleaning that metal oxide for us. Now, how do we do that? Well, what we do is we keep stripping that water out of the atmosphere, okay, pushing any water that forms out the front of the furnace. We want to keep putting in super dry atmosphere gases into our atmosphere. And that's what keeps us tipped. So nature just keeps grabbing as much oxygen off of the metals as it can and hooking it to the hydrogen to form the water. And the reason we talk about dew point is a way to measure the amount of water that's in our atmosphere, right? And so we steal that concept from the weatherman, and we actually take the gas and we look at how much water is in that to tell us which way that scale is tipping. And dew point is really the temperature where the gas is full of water, okay? And as you cool it, the amount of volume in that gas keeps getting lower and lower and lower, and so eventually it has to kick it out at temperature where it has to kick the water out because it can't hold anymore. That's the dew point. And if you go on our YouTube channel, you can see there's a little video that really explains it well. But that's why we use dew point, is just to measure the water, the amount of water that's in the atmosphere, and tip this scale in our favor. Okay, so now let's talk about gap. Okay, so we want a really dry atmosphere, just like we would for our sintering process. But what gap do we want? Well, if we look at the capillary, or when you put a straw in a glass of water and your water crawls up the straw, okay, and you notice if you put a big straw in, it doesn't crawl up as high as if it was a little straw, and it's because you have to lift. The bigger the straw, the more weight you're trying to lift using the surface tension, right? Well, that's what we're looking at. Is if you look at the size of the pore, okay, our porosity versus the gap, our gap size, well, and that tendency to pull it through, our tendency to pull that filler metal through is this blue line, and the volume that you're trying to pull through, or the weight, is the red line. And so what we want to do is, you notice right here where it crosses is right around 0.02 of an inch. That's your optimal gap. 2 to 2.5 thousandths will give you the most amount of filler metal with the fastest pull. Okay. Once you get a larger gap, you can't pull it through. Okay. And you'll see, I've seen people that, okay, they design around a 5 thousandths gap and they get away with it, right? You can get away with it if you have the time and everything's perfect, right? But once you get above that, they start to have, short shots. They can't pull the filler metal through the gap, and so they don't get a good brace. Or if they're too tight, I don't have as much metal there, filler metal, to actually form the bond. Okay. So my optimal is about 2 thousandths. And the way we calculate how much filler metal we want to put on there is we calculate the volume of this gap. So if I had a piece sitting down inside of a sleeve, I would calculate this gap, but I have to calculate it at the brazing temperature. So if we're going to braze at 2050, take into account the expansion of all the components. That gap's going to be bigger than it is at room temperature. Calculate the volume of that gap, and then add about 50%, 1.5 times, okay? And that will ensure that you have enough filler metal to flow in and give you a good bond. And the reason we want extra is, when you look at a really good braze joint, you see these fillets where on the ends of the braze joints. You want to see nice fillets, okay? They're not what gives you strength, but it's what tells you that it pulled through and it gave you a good bond inside. The other thing is, do not put filler metal on both sides of a gap, because then you don't know if it pulled through. because you're always going to have some left on each side. Only put it on one side or put it in the gap, and then that way you can see if it pulls out to one side or maybe both. Okay, so how does this relate to our compact density? Well, gap's important when we put the parts together, but in sinter brazing, we have another problem. All the porosity in our parts act just like little gaps, and they want to steal the filler metal away. So how do we keep that filler metal from going into the gap but not infiltrating the part? Okay, well, what we have to realize is as our density goes up, as the density goes up, the pore size goes down. As the pore size goes down, look at this, it wants to steal that filler metal even more. That flow potential goes up, right? So smaller pores, higher density, that means that part wants to steal the filler metal from the gap. Okay, so how do we stop this, right? Well, if we look at this, here's our plot of our flow, it wanting to steal it versus the volume. Okay, and you see at a real high density, we're down here. Okay, so it's really not going to steal a whole lot, but it's got a pretty strong tendency to flow, right? Or the capillary action is pretty high. But down over here in our 6.5 or so, the tendency is low, but there's a lot of volume in that porosity that you can fill. And so what that means is, okay, in a conventional process, you'd look at it and say, well, that's not a big deal. It's not going to happen that fast, but you're going to sinter. So we're going to be at this brazing temperature and this sintering temperature for like 20 to 30 minutes. We've got all the time in the world for it to suck all of this filler metal in. Okay, so it's really important. We got to look at, well, how do we stop this? Well, and if we look at it, we know that density is important. And so what we did is we have from left to right, we have a 6.0, 6.2, 6.8, and 7.0 density. And we put a tablet on top. And you notice, as we go to the right, you can see that filler metal pellet melted, and the higher density, it didn't infiltrate because it filled the pores and there was nowhere else for it to go, right? And if we section it, you can actually see where at the lower density, it actually went into the part as opposed to the high density where it sat on the surface. So our density is important. So what we want is we don't want a real low density because we've got a lot of time where it can steal it. We'd like to have higher densities so that it fills the surface quickly and holds the rest of that filler metal in the gap. Also, we can play a game with the atmosphere. We cleaned up the surfaces, right? Cleaned the oxides up, everything. We made sure it was all clean. But if you talk to a lot of old timers, they'll tell you, you have to have endothermic gas to sinter braze. Well, not really. The reason it works is if I have material coming in here at about 1,010 degrees Celsius, endothermic gas contains carbon monoxide, CO, about 20%. CO, when exposed to iron at that temperature, the carbon will actually deposit onto the surface and it'll carburize the surface slightly. So by putting a little bit of endo in there, because you've got a pretty stable gas and you're trying to carburize, it only puts a really, really thin film on the surface of carbon on the surface. And now what did we do? We just made the surface dirty. We made the pores dirty. So now if we have the right gap and we make it just a little bit dirty, what we're doing is we tip this rectangle. So now the flow potential is even lower because it doesn't want to go over the dirt, even though those pores are pretty big. So you tend not to steal as much of the filler metal from the gap. Okay. So if we look, what we basically have here is excuse me here, sorry. We have CO present. Okay, we up above here we have no CO, and you notice how it infiltrated, and then we get only at a 7.0 do we see that we didn't get a lot of infiltration. As soon as we put that CO in the atmosphere, look at how you can already see remnants of the pellet, and at our 6.8 we were able to stop it from infiltrating. Okay, so now we don't have to be molding to a 7.0 to successfully sinter braze. Now we can mold to lower densities and still successfully hold that filler metal at that joint. Okay, so as you can see here, the same thing, CO helps us. Also notice there's no flux in here. Now what some folks will do that sell the filler metals is they'll add something in there that likes to get the oxygen and help you clean the surfaces. Don't use that, because what it does is it makes the pores so clean that it starts to you start to lose you don't have control. Okay, so and just to prove that it is a carburizing, it is not, if you read some of the literature, they'll tell you, oh, it's cleaning. No, it's not cleaning. The CO comes down and it actually contaminates that surface, and so and causes it not to flow. And so here we're looking at hardness from the surface as we go in to see. So it should just be a surface thing. And notice we've got a 290 Vickers on the surface. We come in slightly, it's 278. We come in even further, it's 224. That carbon, the amount of carbon that we pushed in there keeps going down. So we really did stop it from flowing by carburizing the surface slightly. Okay, and so here again is another, it's just some more data on that. This is the distance. If we go from edge to center, you can see here the hardness values as we go through that thing. I apologize, these shouldn't be there. So now, so this is the same for the 7.0. So we're seeing 6.8, 6.2, 7.0. We're seeing that same variation in hardness. Okay, so now this is the money graph. Okay, this is the one that really shows us, well, what do we want to be doing? Well, what we're looking at here, this is filler metal infiltration. So how much was stolen, okay, versus different conditions. And so first one is we have hydrogen and nitrogen, and we have flux in that filler metal. And you notice it doesn't matter what that density is, we're always stealing the filler metal, right? It just keeps going up. And if we look, what we really want to be is in this range down here where we're not stealing it. It drops off. And if we look at this black line, which is hydrogen, nitrogen, and our CO, which causes the carburization, and no flux, like I had mentioned, notice once we get above a 6.9, we see that we don't lose that filler metal. Okay, and so there's little to no loss of the filler metal at the gap. It holds it right there. So what we put on there stays, and we can use it. Now, as we go up, you see that if you have the flux, we lose a little more, and it's just but if you have the CO, it works a little better than just having hydrogen and nitrogen by itself. Okay, and why do great big pores not work? I mean, if you look at it, why do we lose control when we have, it's 6.0 where we have big pores, right? Low density. Well, because what happens if I have a real low density, the pores are great big, I don't have enough viscosity of that filler metal when it melts to fill the pore. It wants to fall into the pore and fill the bottom of the pore like it's a sewer. And so now the only thing that pulls that filler metal through is the contact with the pore surface. So I now, instead of filling the whole pore and pulling all of that filler metal through, when I have a large pore, I only have a small amount. So that means now, even though I'm carburizing, even though I have flux, I'm doing all these things to try and control it, I don't have control because the viscosity of my filler metal is overriding all of the tools I have. So we want to be high in density so that we have control of where that's going to go. Okay, and so like I said, flux, you can see here above, if we have here's with flux, you notice that we infiltrate all the way up through, and we even have some infiltration at 7.0. But if we take the flux out, it holds it at the surface at the higher density like we want. So don't use the flux. So now, let's relate this to our sintering process, right? We've talked about brazing. We've talked about the gap. We've talked about having a clean part. We've talked about controlling, getting all the oxides off the part. We talked about, putting a real thin layer of that carbon in the pores and in the joint there so that there's still enough capillary pull through the braze joint, but not the pores no longer have that real strong ability to pull it, to steal it, right? So we, the gap and the chemistries and all of that, right? And cleaning the oxides. But now let's relate this to our sintering process as well. And so I have a schematic here of our furnace, and we have our load and our preheat, our high heat, and our cooling section, right? And if we look at this in the preheat, the first 2/3 of that preheat's where we remove all the lubricants from the compact. And then in this second, as we go from the 2/3 of the way into the preheat to about the beginning of our high heat, that's where we're going to reduce our oxides. But that's also where we're going to hit that 1850 mark, okay, our 1010 degrees Celsius. That's where we're going to start to carburize that surface to keep the base metal from stealing the filler metal. Then we're going to melt. But you notice in normal brazing, we would heat up, hit the melting point of the filler metal. We'd stay there between 2 to 5 minutes and cool off. Here, we're going to heat up to our sintering temperature. Everything's going to melt, but we're going to sit there for 20 to 30 minutes. So there's all the time in the world for that part to steal that filler metal. That's why it's so important for us to control that cleanliness of those pores and control that density so that we don't steal all the filler metal from the gap and not join our parts. Okay, so here we can say it's really important for us to remove the lubricant. Now, we have to remove the lubricant in the right way, though, because if we heat up too fast and that lubricant comes to the surface and it comes into our gap and it dissociates, we're going to form dirt. We're going to form soot, and then we won't bond because the filler metal won't flow in there. So in this process, in the sinter brazing process, lubricant removal is critical. So really pay attention. We want to stay below 1,000 degrees Fahrenheit or below that 545 for as long as we can. In this case, we're saying we want to be a 6.9 to a 7.0. That means we want to be in the delube temperature. We want to be above the melting point of the lubricant, but below that 545 C in that window for actually 35 to 40 minutes, because it takes time for that filler metal or for that lubricant to come out and vaporize. Okay, and that and we've had other webinars and papers and things that if you want some more information, we can provide you with that. But about how to remove that lubricant. But it's really critical you do it at a low temperature. And then, like I say, we have to reduce the oxides, but then we're going to come back in at the 500 or 1010 C or 1850 Fahrenheit, and we're going to use that. We're going to inject some gas in this location that has CO in it to help us to contaminate those or dirty up those pores just a little bit, not enough to deter the sintering, but just a little bit to deter the the capillary from stealing all of the filler metal from the gap. And then finally, we're going to go up to our 2050. Now we should have everything set. We've cleaned the surface. We've reduced the oxides. We've put a little bit of we've prevented it from the base metal from stealing the filler metal from the joint. And now it flows and we form the metallic bond. Okay. So in summary, the key things is lubricant removal and surface cleanliness are critical, right? We have to reduce the oxides in the surface of the filler metal and the base metal. The filler metal must be in contact with the gap. Do not use a flux with the paste or use a flux with the filler metal. Gap size must be calculated at the brazing temperature. Compact density must be 6.9 or greater grams per cc for an iron-based system. We want to carburize the compact surface to limit the flow of the filler metal into the compact. So we hold that filler metal at the joint. And then one thing that's really important, everybody thinks that you can only use like AB72 or these special grades that you're getting different places. You can use copper, and you just have to make sure all of these steps are in place. But if you have a 6.9 density and you're cleaning everything up and you're getting the lubricant out before it can soot, and you're doing all the things that we've shown here, you can use pure copper to Sinter Braze. We've done it. Okay. Also, just a few notes. We are going to be having a number of other webinars coming up throughout the year. Okay, so today's Sinter Brazing. The topics will be announced here shortly for the ones here in the United States, and that will be in April, September, and December. And we have 2 of them planned for March and June in Mexico. Those will be conducted in Spanish for our Spanish-speaking friends. So the troubleshooting and the furnace atmosphere safety will be conducted in Spanish in March and in June. So please, you have a QR code there. Please, scan that and plan on attending some of those. And then the other thing is, we do have a continuous furnace brazing symposium that we put on, and this year it will be, and this is a 2.5-day event, and it will be held in Niagara Falls, New York, and it's May 13th through the 15th. We're offering something really unique. We've partnered with Penn State, and we will be offering continuing education credits. Penn State will be offering the continuing education credits if you attend the symposium. So now attendees of this symposium will actually have a continuing education transcript in the College of Engineering at Penn State, that if you were to go from job or to job, or if someone wants to check, you can actually pull your transcript and show, I attended a continuing an accredited continuing education course, and I have 1.5 credits in the fundamentals of brazing. And then as time goes on, we'll offer other ones as well. And but you'll actually have a certificate from Penn State of completion for the continuing education credits. But you would also have the ability to say, hey, you can check my transcript. I have those continuing education credits from Penn State in brazing. And so that it's going to be $650 per person, but that includes the continuing education credits. So also, those of you who have PEs and need CEUs to maintain your PEs, this works. So that's something nice that we've now been able to work out with Penn State and Abbott, and we'll be able to offer that as well. So please scan the QR code here as well. And we hope to see you in Niagara Falls. Okay. Thank you very much. I really appreciate your time. If you have any questions, I'm more than happy to answer them now. Or if you just want to send them in to us, that's fine. You can just send them in at info@abbottfurnace.com, or you can send them to me. My email's here, sfeldbauer@abbottfurnace.com. I'd be happy to chat with you and answer your questions. Okay.
Thank you, Steve. That was very informative.
So, okay. All right. Do we have any other questions, or?
I don't see anything coming in here, so we'll go ahead and end the webinar. Like Steve mentioned, if you do have any questions, feel free to email him directly, or you can always email info@abbottfurnace.com. So thank you again, and we hope to see you at our next webinar or at our symposium we have in May. Have a good day, everyone.
Thank you. Bye-bye now.
Bye.